Hello everybody, my name is Joe Madura, and I'm going to be presenting some concepts that can be used in ski bindings to protect the anterior cruciate ligaments. The concepts that I'm going to present were all developed through the application of axiomatic design. Grade 3 ACL injuries account for over 20% of serious ski injuries. We have known about these ACL injuries since the mid-1980s, but there is still little mitigating ACL injuries in alpine skiing. The question we have is, can ACL injuries be reduced through the development of new technology, specifically ski binding and plate systems? There are two ACL injury mechanisms. The first is the isolated boot-induced anterior drawer. This occurs when a skier experiences flight in the unbalanced rearward position. As the skier contacts the snow, the tails of the skis hit the snow first, followed by a rotation of the skis downward to meet the snow. The back of the ski boot transfers a force to the leg of the skier, which causes a shearing load at the knee. The second injury mechanism is a combined valgus, angular rotation, and anterior drawer. This is known as a phantom foot, slick catch, or dynamic snowplow injury mechanism. The question is, can we design new technology to help filter the injured loads transferred to the skier? To do this, we're going to utilize axiomatic design. Axiomatic design is a design methodology that leads to controllable, adjustable, and robust solutions, and utilizes a hierarchical structure to break down the functional and physical elements of the design. The two axioms of axiomatic design are Axiom 1, which is to maximize the independence of the functional elements, which leads to controllable designs, and Axiom 2, which is to minimize the information content of the design. This leads to the maximum probability of success. To utilize axiomatic design, we have to identify the functional requirements of the ski binding. The first functional requirement is to transmit control loads from the skier to the ski. The second is to transmit sensory loads from the ski to the skier. And the last is to filter the ingress loads that can be transferred from the ski to the skier. Once we have identified the functional requirements, we can put them in a hierarchical decomposition to identify how we're going to solve the problem. In our decomposition, we start with FR1, which is to transmit control loads, and functional requirement 2, which is to prevent the transfer of ingress loads to the skier. We can apply a spatial directional theme to the transfer of control loads to break it down into different directions a load has to be applied to the ski. The second FR, prevent the transfer of ingress loads, can be broken down using a hazard-based system. Here we see that it's been broken down into the different types of injuries a skier may see while skiing. We have boot-induced anterior draw loads, phantom foot loads, spiral fracture loads, tibial bending fracture loads, and tibial plateau fracture loads. There already have been some binding designs that have been created to address some of the ACL injury mechanisms. Vertical toe releases have been in binding since the early 1980s. The Gatesy binding, developed in 1982, incorporated a vertical toe release. The vertical release was independent of the horizontal release, which allowed for independently adjustable and controllable release mechanisms. The main issue with this binding is that it introduced another release mode and increased the possibility of inadvertent release in the binding. Another design is the diagonal toe seen in Tyrolia bindings. This again allows a vertical release of the toe, but the vertical release is based on a fixed ratio between the vertical and horizontal retention forces. If we apply the principles of axiomatic design to these designs, we can see that the first design, the Gatesy binding, can be adjusted independently of each other. So the vertical retention force is not dependent upon the horizontal retention force. This allows the skier to adjust the two forces to meet his needs. In the Tyrolia design, we see that both the horizontal retention force and the vertical retention force are dependent upon each other. So the skier cannot increase one without increasing the other, or decrease one without decreasing the other. This is what we call a fully coupled design. The issue with this is that a lot of advanced skiers who are afraid of inadvertent release in the horizontal direction will increase the retention force of their bindings. This in turn increases the retention force in the vertical direction and can lead to increased ACL injuries. To address valgus and angular rotation ACL injuries, the knee binding was developed. The knee binding incorporates the lateral release of the heel and introduces another pivot point at the toe of the boot. The heel release load is independently adjustable from the vertical retention load. This allows the skier to increase one without increasing the other. Again, a problem with this binding is that it introduces another release mode, which could lead to inadvertent releases. As we can see, inadvertent release is a primary concern when designing new ski bindings. Safety mechanisms are oftentimes not introduced because they may impact performance and lead to inadvertent releases. Furthermore, skiers are not going to accept a binding if there is an added potential for inadvertent release. The amount of work to release a ski from the skier can gauge the likelihood of inadvertent release, and the more work to release, the less likely an inadvertent release is to happen. This slide shows a load displacement plot for a ski binding as it releases the ski from the skier. As one can see, there's a skiability line. All forces below that are required to transmit control loads to the ski. In between the skiability window and the injury threshold, there is an adjustment window where the ski binding can be adjusted to release the ski from the skier. In the event that the ski is not released from the skier, it returns along this path to its original starting position. Advanced skiers who are afraid of inadvertent release will increase the retention force needed to release the ski from the skier in order to increase the amount of work to release. The issue with this is, before the ski is released from the skier, the injury threshold is crossed and can result in injuries to the skier. A better solution would be to absorb potentially injurious loads by increasing the amount of displacement needed to release the skier from the ski. This would increase the amount of work to release without placing the retention force above the injury threshold. If you look at absorption systems and release systems using the principles of axiomatic design, we can see that absorption systems are more controllable and adjustable than release systems. In a release system, the system to release the skier and the system to retain the skier are not independently adjustable, and this leads to a fully coupled design. In an absorption system, the system to absorb injurious energy can be adjusted first, followed by the system to retain the skier. This allows for a controllable solution. At WPI, we've asked senior design students to design a solution to the ACL injuries using axiomatic design for their senior capstone design project. What they have come up with are binding plates to absorb the injurious energy. These binding plates can accommodate commercially available bindings and absorb the injurious energies in the plate system. So instead of work being done on the knee to tear the ACL, work is being done on the ski binding plate system. These plate absorption systems can reduce energies without the introduction of another release mode, thus cutting down on inadvertent releases. Aside from ACL injuries, we can also absorb other loads and injurious forces in the ski binding system. We can reduce boot-induced anterior draw loads with a rotation in the posterior direction. We can reduce the amount of tibial plateau fractures through a displacement in the vertical direction to absorb potentially injurious loads. And we can decrease inadvertent releases from the heel with a rotation in the anterior direction. This increases the amount of work to release the ski boot from the heel piece of the binding. Students have also developed solutions to absorb phantom foot loads in the ski binding system. Inward rotation loads are absorbed through a horizontal rotation about the toe, much like the knee binding, but instead of releasing the boot, it just absorbs the energy and then returns to the original position. This way, the injurious energy is absorbed without releasing the ski from the skier. This solution here also absorbs boot-induced anterior draw loads with an anterior rotation about the toe of the binding. This movement here may also absorb tibial plateau fractures. As we've seen, with the application of the axiomatic design principles, systems which absorb the injurious energy are more controllable and adjustable than systems which release the ski from the skier in case injurious loads are seen. However, this solution can be made even better by making it situation dependent, so that the design will only absorb the injured energy if the skier is in a potentially injured situation. This way, all control loads can be transmitted to the ski faithfully. We do not know the exact magnitude of load necessary to cause a valgus and a rotation ACL injury in skiing. The load required to cause injuries may be less than the loads required to perform skiing maneuvers. If we create a situation-dependent binding, we can allow the binding to only activate if the skier is in a compromised position. Thus, we're allowing all control loads to be transmitted from the skier to the ski without transferring any injurious loads from the ski to the skier, even if the loads required for skiing are higher than the loads required for injury. If we look at the hierarchical decomposition of a situationally dependent binding plate to absorb inward rotation ACL injuries, we see we've broken it down into three main functional requirements. We have to provide the resistance to displacement of the binding plate, we have to allow for displacement of the binding plate, and we have to detect when the injury is going to occur. The problem is detecting when this injury is going to occur and allowing the binding to react to this injury. Through the retrospective work of others, we've noticed that most ACL injuries occur when the skier is in a back-weighted, unbalanced position. If we can sense when the skier is in this back-weighted, unbalanced position, we can have the ski binding plate change its release and absorption characteristics accordingly to reduce the injuries, while transferring all the control loads when the skier is in a controlled, balanced position. A solution to sensing the back-weighted skier, which we have developed at WPI, is to allow the heel of the binding plate to displace vertically. Upon this displacement, the binding plate will change its absorption characteristics to reduce the amount of injuries seen by the skier. An added benefit is that this displacement will absorb loads which could cause tibial plateau injuries. Upon the displacement in the vertical direction of the heel of the binding plate, the heel of the binding plate is released from the heel of the ski, allowing it to displace inwardly from the ski. A force is opposed to this displacement, absorbing the injurious loads. In this manner, work is being done on the binding plate system rather than on the skier's knee, reducing the amount of inward rotation injuries the skier may see. This slide shows a load displacement graph of the binding plate we have proposed. As you can see, by allowing an increased amount of displacement, we have increased the amount of work being done on the binding plate. This can reduce the amount of work being done on the skier's knee and reduce the amount of injuries. The issue with the strictly absorption system is that we can only absorb so much energy. If the skier is still in an injured situation after we absorb all the energy we possibly can, we can introduce a binding on top of the binding plate, which will release the skier if he is still in an injured situation. In this manner, we can decouple the absorption system from the retention system. That takes care of inward rotation ACL injuries. Boot-induced anterior draw injuries are most common in downhill racing. They can also be seen in Super G and freestyle disciplines as well. But boot-induced anterior draw injuries are rare in the other disciplines and the recreational ski. Because of the rarity of boot-induced anterior draw injuries in disciplines other than downhill ski racing, Super G ski racing, and freestyle, we can see that perhaps a boot-induced anterior draw binding plate system is not necessary for the average skier. But for downhill, Super G, and freestyle skiers, we can create a system to allow an upper rotation of the toe about the heel of the binding. This would absorb the boot-induced anterior draw loads without introducing another motor release. And because the loads needed for boot-induced anterior draw are likely above the loads needed to perform skiing maneuvers, it's not going to become an issue for transferring control loads from the skier to the ski. In conclusion, what I like to propose is that we create bindings which release and retain the boot of the skier to the ski. Then we create binding plates to absorb dangerous loads before the release of the ski boot from the ski. Release bindings can be placed on top of these plates to release the skier once the maximum energy we can absorb has been absorbed. This can result in lower retention and release loads and decrease the amount of injuries seen. We can also create situation-dependent absorption systems that can sense when the skier is likely in an injurious situation. Thank you for your attention.